Hi Chem Gang! In this video I'm going to show you some tips on how to set up your conversion equations when you are converting from moles to grams, or grams back to moles, or moles to atoms and molecules, or atoms and molecules back to moles, and of course the big ones, grams to atoms and molecules back to grams. So just some tips on how to set up your equations, specifically when you're using those conversion fractions or factors. That how do you know what to put in the numerator, the top position of the factor, and what to put at the bottom position, the denominator position of the fraction? So first of all, we have to talk about the conversion factors that we use, and the first one being Avogadro's number of 6.02 times 10 to the 23. That's how many things are in 1 mole. So if you're counting atoms, you're going to have 6.02 times 10 to the 23 atoms in a mole. If we're talking about molecules, you have 6.02 times 10 to the 23 molecules in 1 mole. So this number pertains to anything that you are counting in the mole. The other conversion factor that's useful is that 1 mole of anything is going to be the molar mass of the element on the periodic table. So an example of this would be if you have 1 mole of carbon atoms, the molar mass is going to be equal to 12.01 grams, which is the molar mass found on the periodic table. And as long as you have your periodic table, you can look up the molar mass of any element on the periodic table. All of these conversions can be set up as a conversion factor, which is a fraction. So if we're looking at this first one, you can set it up as a fraction of 6.02 times 10 to the 23 atoms over 1 mole. But you can also set it up as 1 mole over 6.02 times 10 to the 23 atoms. So conversion factors are fractions where you can flip the denominator and the numerator and still use the conversion factor. It's very, very effective no matter which way you put it. Another example, let's look at this conversion factor of 1 mole of carbon is equal to 12.01 grams of carbon. So you can have 1 mole of carbon over 12.01 grams of carbon, or you can put the grams on top and the mole on the bottom. So they're completely reversible, these conversion factors. The question is, how do you decide whether to use this conversion factor or this conversion factor? In other words, how do you decide what to put on top of the fraction and what to put on the bottom of the fraction? So that's what I wanted to clarify today. So let's look at this question. You have 1.56 moles of carbon. Question A is, what is the mass in grams? And B, how many atoms of carbon do we have? So first of all, let's just go with question A. What is the mass in grams? So we always start out with what we're given when we're setting up these equation. So we have 156 moles of carbon, and then on this side we want to put equals and then what we're looking for, and we're looking for the mass in grams. So our conversion is from moles to grams, and we're going to always multiply by a conversion factor. So this is how I set up my skeleton equation for this question. I start out with what I'm given, it's equal to what I'm trying to find, and I'm always going to multiply by a conversion factor. Now the conversion factor that I'm going to use is 1 mole of the substance, which in this case is carbon, which is a singular element. It's not a molecule that we're looking at, it's just plain old carbon. And we know that carbon is 12.01 grams per mole. So that's its molar mass. So this conversion factor we can use either in the form of 1 mole is equal to 12.01 grams of carbon, or we can set it up as 12.01 grams over 1 mole. So which fraction are we going to use? Well, what we are going to put on the bottom has to be the one that will cancel out the moles so that we're left with grams. So whatever we put on the bottom has to cancel out this. So that means we're going to put grams on top. So another way to say it is that whatever we want to convert to, which is this case grams, that also has to be on top of the fraction. So you can think of it in two ways. You can either think of putting what you're going to cancel out on the bottom, or you can think of whatever you need to find has to be on the top so that it does not get canceled out. So that means for this one we're going to use the conversion factor in this form, 12.01 over 1 mole. The moles cancel out, leaving us grams, which is great, and then we just have to do straight multiplication. We're going to take 1.56 times 12.01 grams, and that gives us 18.74 grams of carbon. Okay, let's look at B. Same thing. We're going to start with 1.56 moles of carbon, but this time we're trying to find atoms. So over here we're going to, probably going to need more room than that. Let me delete that. So now we're going to do atoms, and we're going to do a conversion factor, and for the conversion factor for this one we're going to use 6.02 times 10 to the 23 is equal to 1 mole of substance. Because we're looking for atoms, we're going to use Avogadro's number, which is 6.02 times 10 to the 23 atoms, so we're going to leave that on top because we don't want that amount canceled out. And then 1 mole goes on the bottom because that's always going to be the unit that cancels out and is not in our answer. So that's how you decide what to put on the bottom in this conversion factor. It's going to be the unit that you cancel out, or you can think of whatever it is that you put on top is what the final answer is going to be, if that helps as well. Then you're multiplying 1.56 times 6.02 times 10 to the 23. So 1.56 times 6.02 is equal to 9.39 times 10 to the 23 atoms is your answer for that one. Let's do a little bit more complex one, which involves multiplying by 2 conversion factors instead of just the 1. So in my last example, I am going to set up an equation where I'm going to be multiplying by 2 conversion factors instead of just 1. So a little bit more complex of a question. Also, instead of dealing with atoms, you might have heard a bang, that's my cats playing in the background. Instead of dealing with singular atoms such as carbon atoms, we're now dealing with molecules. So we have NO2 molecules, nitrogen and oxygen together as a molecule. So we're looking at nitrogen dioxide molecules. So also we are going from, instead of just one jump from moles to molecules or moles to grams, we are going from molecules and we're skipping all the way over to grams. So that means we need to do a mole conversion and then a gram conversion. So that's another way to think of it using this visual graphic, that if you are skipping from molecules to grams or grams to molecules, you're going to have to do a conversion to moles first and then over to grams. So that kind of helps you map out what you're going to be doing. So for our equation, we are going to use the 4.78 times 10 to the 24 molecules of nitrogen dioxide. And then we're going to use 2 conversion factors, because that's what it takes. We have to go from molecules to moles and moles to grams to get to grams. Okay. So our first one, we have to go from number of molecules to the number of moles of nitrogen dioxide. Remember, on the bottom we always put our number of molecules, or we always put the number that we want to cancel out. So we want to cancel out molecules because we want to get to grams. So that means we are going to put moles on top because we're going from molecules to moles. So the conversion factor we're using is 1 mole is equal to 6.02 times 10 to the 23 molecules. That one is the constant that we know. So we can put 1 mole on top, 6.02 times 10 to the 23 on the bottom, and that's our first conversion factor. So we've converted from molecules to moles. Molecules to moles. Now, and that cancels out our molecules, so now we'll be left with moles. Now we have to go from moles to grams. So we're going to go 1 mole is equal to how many grams of nitrogen dioxide. That's the conversion factor. We weren't given this, but we can figure this out by using the molar mass of nitrogen and the molar mass of oxygen to get the full molar mass of NO2. So before we can put our conversion factor here, we have to look up the molar mass of nitrogen, which is 14.01 grams, and our molar mass of oxygen is 16 grams. So when we do the molar mass of NO2, it's going to be 14.01 plus 2 times 16 grams. So our total molar mass of nitrogen dioxide is 46.01 grams. And then this will be our conversion factor. We want to have grams. We're going from moles to grams, so that means we are going to cancel out moles on the bottom and have our grams on top for our final answer. So that means we're going to put that 46.01 grams on the top and 1 mole on the bottom. Now that our conversion factors are set up correctly, we will then multiply across the top. So 4.78 times 10 to the 24 times 1 times 46.01. That's equal to 219.9 times 10 to the 24. And then on the bottom, we're going to multiply across 6.02 times 10 to the 23 times 1. So that's 6.02 times 10 to the 23 grams. Not quite finished. We now have to divide the top by the bottom. So 2.19.9 divided by 6.02, that's equal to 36.5. And then when we divide 10 to the 24 divided by 10 to the 23, we are just subtracting 24 minus 23 gives us 10 to the power of 1. So that just means we move our decimal over by 1. And that's our answer right there. So 4.78 times 10 to the 24 nitrogen dioxide molecules is equal to 365 grams. So I hope I've helped setting up these conversion factors so that you can cancel out the units to get what you're trying to find. Please go ahead and send me examples through the discussion group, and I'll be happy to show you how to set them up. Thanks so much for watching. Bye for now.